YouTube.
Чего? Можете начинать, все.
Okay, so I'll start. So I have some slides, but probably I will start with Blackboard and wait until the sun comes down a little bit. So the talk is devoted to finite state dimension. So a finite state dimension, first of all, so it maps, so can be considered as a function which maps to each infinite sequence of zeros and ones, a real number from 0 to 1. And so there are several ways to define this. The first way I'm going to talk about is involves entropies of blocks. So the idea is that if you have some infinite sequence of zeros and ones, say alpha 0, alpha 1, we can look some basic statistics in this sequence. So we can look what is the fraction of zeros in the sequence, or we can look also at blocks of larger length than 1, 2, 3, and so on. And look, for example, if you have some block, let's say 0, 0, 0, 0, what is the fraction of all occurrences if we take some very large prefix of our infinite sequence, how many occurrences are equal to 0, 0, 0, 0, and so on. But so on the slide, so there are two different approaches to this. So we can count all occurrences of blocks as here, you know. I don't know if you see, so we can see the blocks of length 4, and we take the first occurrences, the second occurrences, which starts at alpha 1 and alpha 2, and so on. And we can also count, so this will be called non-aligned occurrences, non-aligned blocks. So they can overlap, and so on. And we will also look at aligned blocks. So now the blocks should start at positions which are divisible by the length of a block. Alpha 0, alpha 4, and so on. And so, okay, so I will reproduce this on the blackboard. I want to define what is called block entropy rates. Suppose that I'm looking at for example, the first capital N, let's say, non-aligned occurrences of the block. So I take I uniformly at random from 0 to n capital N minus 1. And then I can consider a random variable which is a function of I, if, which can, so the following random variable, the block of length k, which starts at I. So alpha sub I, alpha sub I plus 1, and so on. And we can consider the entropy of this random variable. So the maximum possible, so this, and this is like, this is what we denote by H and A, capital N of alpha. Okay.
So what is the entropy of binary sequence?
No, it's a random variable. So, you know, we fix an infinite sequence of zeros and ones. Then we have one random variable I, which is a uniformly at random, chosen uniformly at random from this thing. Then we define another random variable, which is a function of I.
I
So,
see.
namely,
I see, yeah.
okay. And so this is for a non-aligned blocks, definition for non-aligned blocks, and for aligned blocks we can define it similarly. But we have to take here the first position of the block should be divisible by the length of the block. Also, it should be length capital I. So there should be ki, so on, alpha sub ki plus k minus 1, something like that. Okay, and now if you want, so now we can take, so now we can define block entropy rates of alpha for given length of a block as the lim-inf of these quantities. Because so now we have h sub k of alpha, for example, for non-aligned case, which is just lim-inf of these entropies as the length of prefix goes to infinity. Yeah. And the same for aligned case. Okay, so, and now let's talk about, before defining a finite state dimension, let's talk a little bit about normality. So now, since I have defined these things, I can just define in these terms what is a normal sequence. So I call a normal sequence, so I call alpha a normal sequence if for all k, if you take these block entropies for blocks of length k, they would be maximal possible. Okay, so what it really means? It means that for every, so this is equivalent to the following definition. If we take any block of length k, then the asymptotic frequency of this block should be 2 to the minus k. So it's a usual definition of normality, but there is also one point here that there are two ways to define normality, and it's not obvious whether they are equivalent. So we can take normality for non-aligned blocks and for aligned blocks. Yes, so here I wrote non-aligned blocks. And this is all the results, but actually it turns out that these two definitions.
Слово aligned, вы где-то в текстах оно встречается, или вы его просто перевели?
Шей не использовал, значит, такое. Это, я не уверен, ну, я как бы...
Должно быть adjustment, ну, length даже.
Окей.
Align вроде бы достаточно стандартное слово в такой ситуации.
Ну вот я просто на всякий случай спросил. Ну,
Я не поручусь, конечно, потому что ощущение такое, что даже так и говорят.
Yeah, so anyway, there are some old results which can be attributed to Pillai or Niven Zuckerman, stating that that aligned normality of a sequence is equivalent to non-aligned normality. So now what I want to tell you, and our first contribution here is like a generalization of these old results. First of all, I can now give a definition of a finite state dimension. So what, in the literature, for example, one of the definitions that were known is the following one. The finite state dimension of alpha is infimum over all k. You take block entropy rate for blocks of length k for aligned case, and you divide it by k. So you normalize this thing. So now this thing is from 0 to 1. And you take infimum over all k. And so this is one of the definitions known in literature, and it was also known, and it seems at least, that this infimum is equal to the limit. Of this thing. So this limit exists and equals infimum of this sequence. And I think in some papers it is said that it was proved by Lempel and Ziff.
Excuse me, does it exist only for normal sequences? Or for
No, so for all alpha. So first of all, definition is for all alpha, and for all alpha this thing equals this limit. And what we have observed, and what seems to be, so we didn't find something close to in literature, that we can also use a non-aligned blocks as well here. But it's strange that it wasn't. So we can have this infimum for non-aligned blocks, and limit also exists for non-aligned blocks as well. Okay, so a few remarks. First of all, from this thing, if you know that, if you have already proved all these equalities, then first thing that it is which is obvious is that a sequence is normal if and only if its finite state dimension is 1, just because of this infimum. The second thing is that from this it is also obvious that non-aligned and aligned versions of normality are equivalent. And and actually finite state dimension defined in terms of aligned and non-aligned blocks are the same. Okay, so I will probably now give a second new definition. So it can be second definition of finite state dimension, and maybe I'll return to the proof of this and some additional results later. So, and the second equivalent definition of finite state dimension, so it's a Kolmogorov style definition, so which can be defined in terms of some complexity functions. So we prove the following theorem, that finite state dimension of a sequence equals infimum over all functions f. I will say what conditions should satisfy these functions. Lim as capital M goes to infinity. So we take it's kind of a complexity of the n-bit prefix of our sequence and define it by divided by n and take lim. So infimum over which functions? So first of all, functions of the form which map finite binary strings to naturals. And actually it is also possible that the value of f can be infinite, so infinity. So, but okay. And should conditions, which conditions f should satisfy? So the most important one is supер-аддитивity. So it should be the case that for all x and y, if you take f of a concatenation of x and y, then this is at least as the sum of f of x and f of y. So this is supер-аддитивity. And another condition, the kind of a calibration condition. So in Kolmogorov complexity, if in plane Kolmogorov complexity, we have some conditions that if we use axiomatic definition of Kolmogorov complexity, that the number of strings of complexity at most n is small. And for prefix complexity, we have that the sum of 2 to the minus complexity of x is bounded by constant. And here we can have a little bit, it's something similar to prefix complexity, but a little bit weaker condition. So condition is that if for all n, if you take 2 to the minus, the sum of 2 to the minus f of x over all x's of length n, so this is bounded by a constant. So now, so we can write that there exists C such that for all n, if you sum this thing over all strings of fixed length, then it will be at most some constant. Okay. So, and now I'm about to prove it. Okay, so anyway, I don't have a proof on slides, so I'll try it just on Blackboard. So the proof, of course, has two directions. let me start with the most, probably the more interesting one. So I want to show that the finite state dimension of alpha is at least this thing. Let me call this Kolmogorov definition of alpha. Kolmogorov definition of finite state dimension. So how can I prove this? So I can do it as follows. So I know that this finite state dimension is infimum over something. So to show this inequality, I just can show that all of these things are at least this thing.
And what is k? This is k times d of alpha? Or
This is this thing. I mean, so I'm claiming that another definition is equivalent. So this is the first definition, this is the second definition. I call it Kolmogorov definition or something like that. Okay, so now I can fix k. And recall what is hk. For example, I can consider aligned blocks. So what is hk of alpha? This is lim of entropies of some distributions. Yeah, so we take the first n aligned blocks and we take their entropy. We take the first n aligned blocks. We take uniformly random block within this first n aligned blocks, and we take the entropy of this thing. And lim of this entropy equals this thing. So lim so there exists a subsequence of the distributions such that limit is equal to this thing. So we can take a limit point here. So let me call the limit point of distributions here eta such that entropy of eta equals this thing, yeah? So, and eta is a distribution on k bits. So, in particular, yeah.
You should write also the subscript k in the right hand side, right?
Yeah, so I want to recall my definition, and I want to recall my notation that I denote if what the entropy which I was talking about of the first aligned n aligned blocks by this thing. So I'm just claiming that I can consider some. So here I have some sequence of distributions, and I can take a limit point such that its entropy is equal to this thing. Now I want to upper bound.
So eta is a distribution on k bits.
Yeah. So by the way, now it seems quite good.
Oh. А так хуже. Хорошо видно, когда никто не смотрит.
Yeah. Okay, so I think that's okay. So that was actually, I don't have the whole proof on the slide, but at least some formulas. So this distribution eta, it is what I defined here. Yeah. And so what my goal is to upper bound this infimum over f's, yeah? So to upper bound infimum, I can define some f so that this thing is small. So Okay. Okay, so I want to define some f such that entropy of eta divided by k is at least, you know, lim_inf as capital N goes to infinity of this thing. So my goal now is to transform eta into f, okay? How I will do this? So I will define so an auxiliary finite state machine, what this machine will do. So I don't know. So basically it will be martingale. So first of all, this finite state machine has states. So its states are elements. So the states of this finite state machines are strings of length less than k. Okay, and what it does? So we can assume that this machine tries to predict a bits of a sequence, of some sequence. And each time the next bit is about to come, this machine makes a bet. So each moment of time it has some amount of money which is denoted by C. And so it splits C in two parts. So one part is her bet on 0 and one part is her bet on 1. But actually, so there is a very specific way how this machine splits its capital. Namely, so if this machine is in a state Q, so Q is a string of length less than K. So what is here eta of 0 condition on Q is just a conditional probability that if the first if the prefix of eta is equal to Q, what is the probability that the next bit is 0? Okay, so if this notation is clear, so the machine just does this thing, okay, so splits in the following proportion. And if so, one bet will be correct, one bet will be incorrect. So the machine earns twice the correct bet and loses the incorrect one. Okay, and so I should also define.
So if the bet is correct, then the machine wins twice the amount of the bet.
Yes.
If the bet is not correct, it just loses the amount of the bet.
Yeah. So. Yeah, so we have two bets. One is multiplied by 2 and one is okay. Okay, and I should also define how the states of a machine evolve. But it's kind of natural thing, so if we are, so basically what machine does, it remembers the last, you know, but no, it's not very correct. So machine works as follows. So if it instates Q, and if it reads a bit, for example 0, then it comes into state Q0. Okay? But remember that the states of a machine are strings of length less than k. So what happens if the length of q is k minus 1? Then machine just comes into state which is empty string. So basically what happens with the states, so it starts to read, if we start with an empty string, yeah, so if the machine in the beginning is in a state which is empty string, so it reads the first k bits and then forgets everything. Then it reads the second k bits and then forgets everything, and so on.
So it's a deterministic automaton.
Yeah. So the deterministic automaton which makes bets. And how I will now define, so now can, okay, so one notation. If I so CQ of x, what is CQ of x? X is a binary string, Q is a state of an automata. And this is how much money earns the machine when it reads x and starts in state Q. If in the beginning the machine has 1, its capital is 1. Okay? This is my notation, and I just want to define f as follows. I don't know, should I erase the theorem here or?
And actually, big F depends on eta, on the distribution.
Yeah, so we want to transform the distribution into f. So I don't know, do you see a formula here? So I should not write it down. So we take the length of x minus maximum of all states of the machine, log of the capital which machine earns on x. So why we need this max? So now we have to check 3 things. So first of all, that this is true. No, let's skip it to the finish. So the first of all, that such f is super-additive. The second thing is calibration property, and the third thing is this. So let's start with super-additivity, the most important one. And you'll see why we need max here. Just, so if you have a concatenation of 2 strings, so then f, let's say, of y and z, and z, it's the length of the string, which is length of y plus length of z, minus a log of the capital for some state q on which the maximum is achieved. Yeah, so I take q which gives me a maximum. Okay, so this will be log of cq of y z. Yeah, I need just one log. Yeah, no, I take q to be the state which achieves the maximum. Okay, so and then the crucial thing is that we can write it as follows. So y plus z minus log. So we can write this capital as a product of 2 capitals. Namely, the first, the machine starts in q, reads y and earns some amount of money. And then it comes into some other state q1, it is not important which state, and earns some money on z. So and now we see that so we can write the log as the sum of logs, and we will have the length of y minus log cq of y, and the same for z, but for some other state q. But what is important, why we need maximum? The maximum is because, so here is some state and here is some state. So at least I can say that this is at least if I take here the maximum of states, and the same for this.
So we have the inequality greater than.
Yeah, we have the equality then. Okay. Okay, the next thing we should verify is the calibration property. The calibration property is that, you know, the sum of 2 to the minus f of x over all x's of the same length is bounded by a constant. So, and what is 2 to the minus f of x? If, let's suppose that we have the length of x is n. So we have 2 to the minus n plus, multiplied by a capital, by maximum of over all states of the capital. Yeah? And the sum of all x of this length. So I can upper bound the maximum by sum. Yeah? So it will be a sum of all states, the sum of 2 to the n multiplied by CQ of x. So now if I fix a state in which I begin, it is just a martingale. So the sum of CQ of x is 2 to the n. So on average, the capital we earn after n games is 1. This is basically this. So, and this can be bounded by some constant, namely by the number of states, which is 2 to the k or something like that, but this doesn't depend on it. Okay? Or I should be more specific about this.
Yeah. Please be more specific.
Okay. So, you know, so, okay, so we start with capital, in the beginning we have capital 1, yeah?
Yeah.
And we split it capital in 2 parts. Let's say A and B. So if we have 0, then our capital will be 2A. And if we will have 1, our capital will be 2B. So, and recall that A plus B equals 1, because it's a proportion in which we split our capital. Yeah? So you can notice that the sum over strings of length 1 is equal to 2. And then you proceed by induction. You can notice that by each level increases the sum by 2.
Yeah.
So this is also.
We are now consider an alignment case.
Yeah, we are in a line case.
Well.
Okay, so and the third thing is.
And below depends on k. Constantly below notation depends on k.
Yeah, depends on k.
But we didn't use yet that the machine goes to the empty state, the state for the empty string after case set.
Oh.
Yeah, we didn't
You
use that.
haven't used it. Yeah. So
Yeah, we will use this in no, we didn't. We are not finished because we have to prove this. Okay, so to prove this, so namely, so okay, so what is f of this thing? So first of all, as I want to upper bound this limit, so I can take any subsequence which is or maybe not. I can take any subsequence which is convenient for me and take the limit of this subsequence. So anyway, so what is more important here is that, so this is, let's assume that capital N is divisible by k. Yeah? So then what is it? So it will. So in the numerator we will have n minus max over all states log of the capital. Yes. But now I want to forget that here I have max, yes? So if I want to upper bound the limit, I can upper bound it by, I can just take here empty string now. I assume that I start with empty string. Yes, so for simplicity. So if I now start in empty string, what basically happens with my capital? So namely, you know, I read the block of length k, and on each block of length k, I do the same things, yeah? Then I forget everything and I do the same thing again. And so how much, so suppose that I have a block x, yes? So how much do I earn if I see x? So this is why I need a transition into empty state. So now after that I begin doing the same thing.
If you multiply those numbers, I mean,
yeah, I just
you obtain the probability of them.
Yeah, and I also obtain 2 to the length of x multiplied by eta of x. Yeah. So yeah, and okay. So and the whole capital will be the product of all blocks, overall blocks I have in my sequence. So what it will be? It will be n minus log of the product. So okay. So now if I fix the block x, okay. So how many times so let me denote. So I can count how many times this blocks appears within the first n aligned blocks of length k. And let me denote this thing by f of x multiplied by n over. So okay, so we have here n over k aligned blocks, yeah? So I should multiply it. So namely by f of x I denote the fraction of these blocks. So the number of blocks is f of x multiplied by n over k. And here I have this thing, yeah? So 2 to the k, because the length of x is k, eta of x. And I should divide it by n. So if I'm not mistaken, then we should be done, because then I just rewrite log. So I will have n minus, okay, the sum of all x's, f of x on n over k, yeah, and here I have k plus log of eta of x, yeah. Okay, so now this and this cancels out because k cancels out and the sum of frequencies is 1, so n minus n is 0. Okay, and here I have something which resembles entropy, yeah. So namely this n and this n cancels out, so I have, okay, 1 over k, and then the sum over all x's, frequency of x multiplied by log 1 over eta of x. But then I just recall that I can take a subsequence in which f of x converges to eta of x. And this will be the entropy of eta over k. This is the first direction of the theorem. So now we can recall what is a theorem, yeah? Probably. So I have proved that this is at least this. Now I want the other direction. Okay, it's much easier actually, but it's not, this is also not very hard. But okay. So now I just use super-additivity. So I have to show that for each f which satisfies these properties, we have that this lim is at least finite state dimension. Okay, so namely I will show that, so namely I can now use a limit definition of finite state dimension. So I will show that lim of f over n, it's not very correct, but is at least lim of block entropies. Okay, now I again work with aligned case over k. Okay. So why is that? Because, well, I need to upper bound this, so I can just use super-additivity and rewrite it using blocks. So I can divide my into n over k blocks of length k. Yeah. So
finite state dimension is defined using just entropy.
yeah.
So and you need now to transform from these super calibrated functions to entropy.
Yeah, but there, yeah.
You have certain function which is.
I will show that this thing is bounded below by entropy just by using log sum inequality. Actually, it's easy. It's easy, and I can even. But probably you understand what. But okay, so now I can upper bound this is this. Now let's say that the first block, let me denote the first block of length k by x1, and so the last block x n over k by n. So now once again I can rewrite this as the sum of all values of blocks of length k, how many time x appears here, exactly f of x multiplied by n over k, where f of x is again a small f of x, it's a frequency of x within the first n over k. Okay, so and you divide it by n. So I can. So I'm claiming that this is at least f. So I take the entropy of f minus some constant here. Okay. So what I have done? So I claim that this thing is at least this thing. Why is that? Because of the log sum inequality. But I don't know, maybe everybody sees why is that. and I should not explain.
Gibson equality.
Yeah. So why? Okay. Okay. If stop me, if I'm explaining too much. So I want to show that the sum minus c is smaller than this. Yes? So I can put it from the right hand side to the left hand side. And if I put it from the left hand side to the right, so I need to show this, okay? For some constant c, yeah? So, okay, so now it's at most log of this, and by calibration property, we have the sum over blocks of the same length is at most constant, which doesn't depend on the block length. Yeah? Yeah. Oh,
Yes, in a sense.
I don't know.
So we can have c equals.
Yeah, we should normalize these powers of 2.
Okay, yeah.
And actually, using the calibration condition, it gives some constant.
Yeah. Because constant is not necessarily 1. Okay.
Relative entropy is bounded, yeah, but by some value depending on k.
Yeah. So, and if we take
C also depends on k, yeah?
C does not depend
Oh,
on
no,
k.
C doesn't. But how?
Okay, so if you take lim of this, so we will have 1 over k because capital N cancels out. And then we will have block entropy rate minus c. Okay? So we have so
Actually, instead of c, we should write log c. But it's
Yeah.
not important.
log c.
Everywhere is factor, so yeah, it's the same constant.
And also there, in that last line above,
Yeah.
in Gibson equality.
Okay, so and I obtain this for every k. C doesn't depend on k. So if I take the limit, this becomes this. So the theorem seems to be proved. Okay. So why this thing is why is convenient? So using this theorem, this characterization, I can give a convenient sufficient condition for normality and reprove some old results about examples of normal numbers. So let me do this. Okay.
Самое время спросить, кто это понял. Шем тут издевается над вами. Кто понял? Поднимите руку. Не, я понял. Я думаю, что я понял.
А что вы, например, не поняли?
Have you understood the proof?
Yeah, it's just the last part which is pullback liveliness, and that I forgot some definitions. Yeah. But the last step I understood everything.
And what step? So here?
Yeah, there.
Okay, so we use the calibration property that
So we use the property that the log function is 12k.
yeah.
So the average of log is at most log of the average. Now f of x cancels.
Okay.
And now
the sum of 2 to the minus f of capital F of f is bounded by
Outside
C.
of C, okay, yeah.
Yeah. So now, what is my sufficient condition? Sufficient condition is the following. So I can consider, let me take any sequence of finite binary strings. Okay, so x1, x2, x3, and so on. They need not to be, so namely, I assume that they are not of the same length, their length grows as n goes to infinity and so on. So, and I want to give a sufficient condition to show that if we take concatenation of all these strings, then these strings will be normal. Okay, so what is this condition? So first of all, we can define the average length of the first n strings, which is here ln, or the sum of.
Еще Шейн говорит, что Шейн claims that the whole proof can be expressed in terms not martingales, but just measures, and it would be more easy to understand.
But just what?
Measures. So martingales is more or less the same as measures.
I see, I see.
So somehow you had a measure, then you transformed measure into martingale using betting strategy,
Yeah.
and then you transform martingale into semi-additive function.
Yeah.
But you could, of course, just start with a
But it's hard to write down this
and
measure.
And the second thing, Shane claims that you have hidden all the motivations. So what are motivations? Motivations for definition, I guess.
I don't know.
Okay.
Motivations of what?
So Sasha, he doesn't know motivations. He hasn't hidden them.
I don't know. For example, I'll give a motivation one. Okay. So now, so the average length of the first 10 strings is denoted by ln sub n, and I can also take what I will denote by h of n. So this is just, you know, you take the first 10 strings and you take a random number from 1 to n, and you take the ith string and you take the entropy of this random variable. So for example, if the first n strings are all different, then this entropy will be log n, okay? Where I is chosen uniformly at random from 1 to n. So I just want to look how many strings appear twice, thrice, and so on. Okay? And I also have some mild assumption on the length of these strings. So the first assumption is the average length goes to infinity. And the second assumption is that the length of each next sequence in each of each next string in the sequence is small o of the length of all previous sequences. And the third assumption is that the maximum length, if you take the first n strings, then the maximum length is sub-exponential in average length. Then it holds that the finite state dimension of this concatenated sequence is at least lim of this, if you take entropy multiplied by average length. Okay, so now motivation. So assume that we have proved this.
But wait, so we are given a sequence, a finite sequence.
No, infinite sequence
Infinite.
of binary strings. So for example,
Infinite sequence of binary strings of different lengths.
yeah,
Maybe.
yeah, like temper noun number. Do you know this?
It's just sequence of all numbers.
Yeah, so we take all natural numbers written in binary. And x1 is 1, x2 is a binary representation of 2, and so on. So here's the instructive example. And temper noun it was kind of the first example of a normal number, explicit normal number. So how can we prove this easily with this sufficient condition? So, okay, so first of all, we should count the entropy of the first n elements of a sequence, but it's just log n because they are all different. It's easy. The second thing
But what is the goal? To prove that concatenation
is normal number. Yeah, okay. So I don't know. Does it count as a motivation, or I don't know. So and the average length, if you take the first n, so the length of a binary representation of the number I is log I plus constant. So the average length is log n plus constant. You can, I don't know, you can take integral or you can use. So I don't know. Does is anybody convinced that this is true?
And what was the assumption about the average length?
So the assumptions are that average length goes to infinity as n grows. It works. The second assumption is that the length of each next string is bounded by, so it's small o of the sum of lengths of all previous strings.
And what's the sum of length?
Okay, so you take the first n natural numbers, the length is about, the total length of is n log n, and the next has log n bits. So it is surely true.
No, it's not true.
Why not true? So this thing is log n, and
Log
this
n.
thing is n log n.
N log n, I see.
Yeah, and the third thing is that the maximum length is at most is sub-exponential in average length. So this is true because the maximum length is log n and the average length is log n.
N is log n, so you obtain n to the...
So the restrictions are that the average length goes to infinity, that it is impossible that you have a string now which, so suddenly comes a string which is much longer than all previous strings in common. And the third assumption is the average length is, the maximum length is not too big.
So all the conditions are
Just
amply true for Champer norms.
yeah, easily. So it's just technical.
Except maybe the first one, because it tends to infinity, but very slowly.
Okay,
Okay.
but we just need that it tends to infinity. So we have proved that Champer number is normal. The next example is Copeland order theorem. So for example, we can ask, so if we take all natural numbers, so for example, what if we take all prime numbers? Is it also true? Yeah, and this is true. And
So prime numbers are dense.
yeah, prime numbers are dense because n over log n. So the theorem is that proved by...
It's an unusual sense of density because...
Okay.
Okay.
So I wrote in the sense, okay. So if I take an increasing sequence of integers, then, and if the number of the elements of the sequence which are at most n is so you know n to the power 1 minus small o of 1. So it means that you know if we have square root of n, it is bad, or n to the power 2/3, it is also better. But if you have something like n log n, then this is good for us, okay? Because this is n to the power 1 plus small o of 1, okay? So then the sequence is normal. So it was proved by...
What does it mean positional representation? Positional representation.
Binary representation.
Binary or ternary?
No, binary.
Only binary.
I mean, okay, so yeah, it
So
works
the
for...
base matters here.
No, it doesn't matter.
Doesn't.
So I assume that also it can be, all this can be translated not only into binary case, but okay.
So it's generalization of Chamber norm, right?
Yeah. So why is this true? So once again, we have the entropy log n of the first n elements. Because
this condition.
Because they are strictly increasing, so they are all different. And the second thing is that, you know, the length, or if you take the nth element of the sequence, so on one hand, so if you take the nth element of a sequence, so it means that, you know, there are n elements of the sequence which are at most xn, x sub n, yeah?
So you're trying to prove the second condition, that the length
Or
is
average
bound.
length is log n.
Intuitively it's clear because if the sequence is growing very fast, then it can't be dense, right?
Yeah. I have like a formal proof, but if you satisfy...
Okay, proceed with the formal.
Okay, I'm just noticing, I want to prove that the length of the binary representation of x of n is this thing. If we prove this, then we're done. Yeah? Because we just multiply everything by 1 plus small of 1.
Sorry, why entropy is log n?
Because the sequence is strictly increasing and they are all different. So if you take, you know, if you have n different strings, you choose one uniformly at random. They are all different, so the entropy is log n.
Oh, I see. All these binary words are different.
Yeah.
Uh-huh.
Yeah.
Uh-huh.
Okay, so why the length of xn is this thing? Very easy, because you know the number of elements of our sequence which are at most x sub n is n. This means that n is xn to the power 1 minus small o of n. And if you take logs, it means that log n is 1 minus small o of 1 log xn. Log xn, its length.
And why the second equality holds?
Because n is the number of elements of our sequence which are at most xn.
Yes.
We know that the number of elements of our sequence which are at most some number is this number to the power 1 minus small of 1. So it's kind of reversed. So n here serves as xn. So we obtain that log xn and log n are equivalent as n goes to infinity. You know, the fraction tends to 1. Okay, so now complement Erdős theorem is proved, and I should also notice that.
Wait. Why it's proved?
Ah,
Because it's not easy to understand because the assumptions are on the previous slide.
yeah, okay. So one. So remember the most important assumption that entropy over Ln should tend to 1. And these assumptions like, so average length goes to infinity, log n. This is also true, so each xn is about log n bits. Yeah? And this is also true. The average length is log n, and the maximum length is log n.
We get small o of log n in the third condition.
You know, so we have to verify that log n is 2 to the small o of log n. So this is true. You know, the bad thing is the maximum length is exponentially bigger than the average length, but it's not the case because they are equal. Okay?
So, and what about the conclusion? So we know then that the final state dimension is at least what?
At least limit of this sequence.
Which is 1.
Which is
in
1.
our case.
So final
So
state
final
dimension is 1.
Which is the definition or not the definition of the normal series?
It's
Which is
almost
equivalent
definition.
by our theorem, but by your theorem.
No, it's, well, it depends on which definition you take. If you take infimum of entropies, then it's obvious that this is true. Yeah? If each entropy is maximal of blocks, then the sequence is normal. Yeah, so it's okay. And so another example, maybe more interesting. What happens if you take all perfect squares? And you
Perfect square.
huh?
Just square. 1, 1,
Oi.
4, 9,
Okay.
16.
Yeah. So now the previous theorem doesn't work. So and I want to okay, maybe let's.
Because it's not dense.
Yeah, because it's not dense. But we can do some trick. So basically, what we have, so the idea is that if you take the first n numbers, natural numbers, they are kind of random, yeah. And if you take if you take a dense subset, then it's also random. But you know that if you take a k-bit square, so its length will be 2k, yeah? Of, you know, I mean, if you take a k-bit number x and you square it, then the square will be 2k bits. So we will split the first part, so we will show that we will use another splitting. We will split, we will consider separately the first half of squares and the second half of squares. And we will show that the first half and the second half of squares depend randomly in some sense.
Are independent?
No, I mean they behave randomly. Yeah. So more precisely what I can show, so okay, so if I so I write down all squares, yeah? So I write down 1 squared, 2 squared, 3 squared, and so on, n squared, and so on. So namely, okay, so now assume that I is a k-bit number. So what I have to, okay, so now, okay, so I assume that I is a k-bit number and I want to define, namely, and so let yi be the first half of I squared and that y let it be the second half of.
Yeah, so which condition of your theorem doesn't work with squares of your general theorem?
It's not dense.
No,
I have the
okay,
first one.
okay.
The first one, not
This
this one.
one, this ratio goes to 1/2.
Sorry, yeah.
So I need a little bit another splitting. So namely, I split each square into 2 equal parts. Namely, if I is a k-bit integer, then let me define yi and zi as follows. So zi is the less significant k bits of I squared. Yeah? And yi is equal to the k most significant bits of I squared. So my sequence will be now yi zi and so on, yn zn and so on. And this will be my splitting for which I will use my theorem. Yeah?
So x is, we just consider x1 being y1, x2 z1 and so
Yeah.
on.
Yeah.
But if I is less than, say, 2 to the power k, I squared has y, the first part is 0, and in the sequence of squares there are no zeros. You just throw one
So
square.
how do you choose k?
K is the length of I.
Ah,
So
k is not fixed.
Ah,
yeah. I mean, okay, so it can be that I is just all zeros. But okay, then we just write them as all k zeros. Okay, so now we have to check the average length at first. Now it's easier, yeah? So the average length is log n, once again, because, you know, the length of zi is log I, and the length of, I mean plus constant, and length of yi is log I plus constant. Okay? So the average length is log n. Okay, so now let's proceed to entropy. Now, so I have the entropy. So for example, I take the first 2n strings, elements of our sequence, and I take them uniformly at random.
So what do you take uniformly at random?
The number from 1 to 2n. And I take the random element of my sequence. So I have a sequence y1 is z1 and so on, yn, zn, and I take a uniformly random one. Yeah?
Hn is defined as the entropy of xi where I is chosen uniformly, right?
Yeah.
So you choose I uniformly from numbers from 1 to
2n. Yeah.
2 times n.
Yeah. The first observation I want to make is that so entropy is concave. Namely, the entropy of this x, y. Yeah. So if I take
Is at least the arithmetic mean of
the arithmetic mean of 2 entropies, if I just take a random y, and if I take a random
z sub I.
z sub I, okay? So I can lower bound entropies separately. So it is easier to lower bound y because, you know,
So y is significant bits.
yeah. So I just claim that, you know, So I claim that the entropy of I given yi is small. It's O of log n. If this is the case, yeah, so assume that we have shown this. This means that entropy of the conditions should be big, yeah, because the entropy of y is log n. Then it means that the entropy of condition should be at least log n minus log n. Okay? So why is that? Because I just claimed that, you know, there is at most log n, O of log n different i's which can give the same yi. Why is that? Because if you fix k, so there are log n possible lengths, yeah? And for each length we will show that there is at most constant number of y's which can give me yi, some fixed yi. So why is that? Because if you fix k, then the difference between two squares, if two squares are k-bit numbers, then the if squares this two squares of two k-bit numbers is at least so I1 squared minus I2 squared is omega. So okay, so formula is I1 minus I2.
Sasha, so what do you want now to prove? That given a square, you can almost determine what?
Given the first half of a square,
Yes.
I can determine the whole square.
Ah, the whole square.
Yeah. And I'm explaining why is that. Because if I fix length, then the difference between two squares, where I1 and I2 are k-bit numbers, is at least the difference between yi and y2 multiplied by the subset is at most 2 to the k. So it will be omega of this, yeah? The difference between I1 and I2 multiplied by 2 to the k. But if you fix the most significant part, then the difference between 2 is at most 2 to the k. Maybe multiplied by 2, because this cancels out if this is the same, and we have also only difference here. Yeah, so this can be only constantly many different i's which can produce the same yi. And this, but okay, maybe, and we have the constant for each length. There are log n lengths if you take the first n squares. Okay. So this is proved. Now I have to prove a little bit about z. So now I cannot say that it is always true that the least significant part determines almost uniquely the whole square. Well, because like if you have 0, 0, 0, then to obtain 0, 0, 0 in the end, we just have to have k over 2 squares in the end. So there will be a lot of numbers which produce this thing. But the point is that this happens very rarely. So namely, so my goal is to show that entropy of I given that sub I is O of log n.
Just the same, but
the argument is different.
the arguments are different.
Yeah, so I need the following lemma. So I claim that, okay, so now assume that I fix some number a. And I want to count the number of solutions of this equality, where x is from 0 to the k. Okay, so how many reminders satisfy this equality given a? I claim that this equality has at most 2 to the t of a solutions where t of a is the maximal d such that 2 to the d divides a. Okay? So t of a is just the number of zeros in the end of a. So this is my lemma. Okay? If the
and because on average t of a is small,
yeah,
so
it will be
have small entropy.
yeah. So why is that? Because if this is true, then 2 to the k divides x minus a multiplied by x plus a. It means that okay, this is just by definition, but it means that there are u and v which sum up to k such that 2 to the a divides x minus a and 2 to the v divides x minus plus a. Okay? Now, if I just sum, or maybe if I take this thing minus this thing, then the resulting thing will be 2a. Yeah?
Okay.
2a is equal x plus a minus x minus a. And this thing is divisible by 2 to the minus or minimum of u and v. And this means that a is divisible by 2 to the minimum minus 1. Okay? And by definition, what it means that minimum of u and v is at least t of a minus 1. Okay? So because t of a is the largest integer such that 2 to this integer divides a. But it means that maximum of u and v, so minimum of u and v is either u or v. But then the other number is at least k minus t of a plus 1.
And what is b?
B?
Yeah, we have any b here.
Where is b?
And you said, no, say it again. Mean is at most t of a minus 1.
Okay,
right?
then max of uv
Is at least
k minus t of a plus 1.
Okay.
Maybe here I should have plus 1, but it doesn't matter. Okay, then, but remember that either x minus a or x plus a should be divisible by 2 to this thing. Yeah?
Why?
Because 2 to the a divides this and 2 to the v divides this. It means that x plus I should, for example, should be divisible by 2 to the k minus t of a plus 1. It means that there are, since there are 2 to the k reminders, modulo k.
But wait. X plus a, for example, is divisible by that thing.
Yeah.
And
It means that all x's which can satisfy this property, they should be separated by this number. So two consecutive consecutive x's which satisfies this property should be of distance at least this thing from each other. I mean, okay, so x1 plus a is divisible by 2 to the k minus t of a, yeah? Suppose that. And x2 plus a is divisible by 2 to the k minus t of a. It means that the difference between x1 and x2 is divisible by this thing.
K minus t, right?
Yeah.
Uh-huh.
So, and this
So
means...
the number is then at most 2 to the t.
Yeah. So given this lemma, it's now very easy to show this thing. Well, because, you know, okay. So, if you know zi, what you need to specify I also. For example, we can, for free, so we need log n bits to specify the length of I. Yeah? So we can do that. So now assume that we have specified the length of I. So let's count how many possible i's can produce that I. So namely, so we know that I squared is 2 to the k multiplied by sampling plus zi, and assume that some other number also squared gives me 2 to the k multiplied by something plus z sub I. It means that j squared equals I squared modulo 2 to the k. That is, there is at most, if we fix k, there is at most t of I such, 2 to the t I such solution. So we need 2 t of I bits. So we need log n bits plus this number of bits. But the average is constant of this thing. So we obtain this. Okay, so probably I should finish now.
Okay. Okay.
Все.